Welcome to the Deep Dive, where we plunge into the most groundbreaking research and emerging technologies to give you a real shortcut to being exceptionally well-informed. Today, we're tackling one of medicine's really profound and persistent challenges. How do you precisely distinguish healthy tissue from cancerous tissue? Especially, when examining critical samples like breast biopsies, we often think of imaging, right? Looking for visible changes, anomalies. But what if the real answer, the truly definitive answer, lies in something much more fundamental, something almost invisible deep within the structure of the tissue itself? So this deep dive is all about a truly fascinating study. It marries cutting-edge microengineering with the elegant universal mathematics of scaling laws. Now, these aren't just abstract equations. Scaling laws are principles that govern, well, everything from how river networks branch out, how trees grow, to, surprisingly, the growth dynamics of living organisms, and that includes tumors. Our mission today is really to unpack how these seemingly abstract concepts, when you pair them with tiny, custom-built biochips, are being used to create a novel and remarkably accurate method for characterizing breast biopsy tissues. It's really a story of science discovering cancer's hidden electrical blueprint. Our guide for this exploration is a meticulously crafted research paper titled Bimodal Characterization of Breast Biopsy Tissues Using MEMS-Based Biochips Toward Improved Tumor Delineation by G.K. Anil Vishnu and his brilliant team of researchers. I'm your host, thrilled to be your guide on this journey into some really innovative science. And joining me, as always, to connect these intricate details to the broader landscape of scientific discovery is our resident expert.
It's great to be here. What immediately grabbed me about this study is how it provides a quantifiable, almost mathematical description of these complex biological processes like tumor growth. It's not just observing, it's actually measuring the very fabric of disease. For you, the listener, this deep dive offers a shortcut, really, to understanding a potential game changer in diagnostics. We'll uncover how subtle, almost imperceptible electrical differences, when precisely measured and meticulously modeled, can unlock critical, unique insights into tissue health. This really challenges us to think, can we redefine how we classify tissues, moving beyond purely visual observations to a deeper, more fundamental, and, well, ultimately more reliable understanding of their intrinsic properties?
That's a powerful challenge, and it's really where our exploration begins, doesn't it? Let's dive into this foundational science, starting with these scaling laws. You mentioned them, but what exactly are we talking about here?
Well, think of them as sort of the universe's secret mathematical grammar. They're universal principles that give us a quantifiable description of complex physical and biological processes that show what we call scaling behavior.
Scaling behavior, like how properties change predictably as the scale changes.
Exactly. They reveal a kind of hidden order in systems that often look chaotic on the surface.
And these aren't just like theoretical ideas, they actually show up in the real world.
Oh, absolutely. They pop up everywhere.
Yeah.
From electrical transport in disordered materials, think advanced composites, all the way to the growth cycles of living organisms.
It's pretty incredible how often nature seems to follow these underlying patterns, isn't it? Regardless of the specific system or the scale.
It really is. It suggests a kind of deep interconnectedness. And what's particularly fascinating here and more recent is the discovery that such a scaling law can also be applied to tumor growth dynamics.
Tumor growth, so not just rivers and trees.
Right. And this isn't just a coincidence. It suggests there's a fundamental, quantifiable difference in how cancer cells proliferate compared to normal cells. It hints at an inherent mathematical blueprint, almost a growth code, even for something that seems as chaotic as cancer.
Wow. A growth code for cancer. What are the implications of that?
Well, it's profound. It suggests there might be deeper shared mechanisms across different cancers. If we understand these universal rules, maybe we can disrupt them more effectively. It changes how we see cancer, from just a biological error to a phenomenon with predictable dynamics we can learn to exploit.
Exploiting quantifiable dynamics. I like that. Not just chasing symptoms, but understanding the core principles. So how does this apply to something as complex as breast tissue then?
Well, biological tissues aren't simple. They're incredibly complex composite materials made up of various substances, biopolymers.
Yeah. Our bodies are astonishingly designed. Breast tissue specifically, you mentioned epithelial cells, stromal cells.
Right, and the extracellular matrix, it's mostly collagen fibers and fat cells, adipocytes. It's a very organized yet complex environment.
So a composite material.
Exactly. And material science tells us that composite materials are well known as disordered systems. They aren't perfectly uniform. Their components are arranged in complex, often irregular ways.
So breast tissue, being a composite, is naturally a disordered system.
Precisely. But here's the critical insight from the research. While both normal and tumor tissues are disordered, they differ significantly in their extent of disorder. It's not just present or absent, it's the degree that matters.
Okay, so how does that disorder change in tumors?
The study points to specific changes during tumor genesis. You get more
Mm.
fibroblasts, fewer fat cells, and the extracellular matrix, the collagen scaffolding, undergoes remodeling.
Remodeling, what does that mean?
It means increased density, more cross-linking, but also structural degradation of the collagen fibers themselves. Interestingly, normal tissue actually has a higher volume of collagen fibers. The tumor architecture is fundamentally compromised.
Right, so the structure is breaking down, becoming more disordered. How can we measure that disorder?
That's where the electrical transport study comes in. It's a really powerful tool. They focus on direct current DC transport. Under DC, the collagen fibers essentially form the conducting network. The cells, with their lipid bilayers, are mostly insulating.
Ah, okay, so the collagen acts like wires.
In a way, yes. So any structural differences in those collagen fibers, their arrangement, their integrity, will directly translate into measurable changes in DC conductivity.
So we're using electricity to probe the microscopic architecture, looking for cancer's electrical signature by checking the collagen network's integrity.
Exactly. It gives us an electrical window into that disorder.
That's a fundamentally different approach. It really sets the stage, suggesting if we can measure these electrical differences accurately, we might identify cancer in a new way. Now, people might be thinking, hang on, don't we already have ways to look at breast tissue? Mammography, ultrasound, MRI.
Absolutely. And those are invaluable tools, no question. They save lives. We also have microwave sensing, microbubbles.
But for these tiny biopsy samples, the ex vivo ones, you're saying current methods sometimes fall short.
For classifying them with the absolute highest precision, yes. They often rely on macroscopic models, averaging things out. They don't fully capture those microscopic structural differences, that subtle breakdown in the collagen we just talked about.
Like looking at a map of highways but missing the local roads.
Precisely. You miss the intricate network. We need a way to correlate the electrical behavior directly with that underlying microstructure for better classification.
And this is where the MEMS-based biochips come in, Micro-Electro-Mechanical Systems.
That's the innovation here. These are tiny integrated devices, mechanical and electrical functions all on a microscale.
Yeah.
Smaller than a grain of rice, incredibly precise.
And the team didn't just design a chip, right? They built the whole platform.
Yes, a tabletop platform integrating these biochips for bimodal characterization.
Bimodal, meaning two modes.
Right. Temperature-dependent and frequency-dependent electrical transport. Looking at both DC and AC properties in different conditions, this gives a much richer, more comprehensive electrical fingerprint.
Okay, tell me about the chips themselves. What's on them?
The two key things. First, interdigitated electrodes, like tiny interlocking fingers making precise electrical contact to measure both DC and AC properties.
Okay, like little electrical probes.
And second, an integrated microheater, a tiny heating element right on the chip to control the tissue temperature precisely for those temperature-dependent studies.
How do they even make something that small and complex?
It's sophisticated microfabrication. Starting with a silicon wafer, adding layers oxide, photoresist patterning with light, depositing thin metal layers like titanium and platinum for the electrodes and heater. It's like nanoscale 3D printing, really precise.
And the scale, how small are we talking?
The whole chip is maybe 7 by 12 millimeters. But the active area, the part that touches the tissue, just 0.34 by 0.34 millimeters. Tiny.
That miniature scale allows for incredibly localized measurements, right? Focusing on the microstructure.
Exactly. And that precision extends to the whole platform. It has an actuating mechanism, like a robotic arm, to position the biochips very precisely onto the tissue sample, essential for consistent measurement.
And I read something about modularity. That sounds important, practically.
Hugely important. The biochips attach to indenters with slide-fit contacts. This means you can quickly swap out the sensor for each new measurement.
So no complex reassembly or contamination issues, like changing a lens on a camera.
Exactly. Makes it practical for handling multiple samples efficiently.
And the electronics controlling it all sounds complex.
It is quite sophisticated. A master-slave microcontroller setup using Arduinos, a Mega, and an Uno controlling movement and data acquisition. There's a graphical user interface, a GUI for commands. Specific circuits handle the DC resistivity, an impedance analyzer connects for AC measurements, and pulse width modulation controls the microheater voltage very precisely to hit target temperatures up to 37 degrees C in this study.
Body temperature. Makes sense? How do they know when they have good contact?
Clever trick? The indenters move towards the tissue until the system detects a distinct drop in measured resistivity. That signals good, stable electrical contact has been made, ensuring reliable data.
Okay, so we have the tech. Amazing chips, precise platform, but how do we interpret the signals? Turn current into insight. That's the modeling part, right?
Right. The modeling is key. They treated the breast tissue as a two-component system. You've got the cells, mostly insulating because of their lipid bilayers.
Like little barriers.
And then you have the extracellular matrix, the ECM, where the collagen fibers form the main electrically conducting network.
The wires again?
Sort of. And the complex nature of this lends itself to percolative-type electrical transport.
Percolation. Like water through a sponge,
I'm
finding paths of least resistance.
Exactly that analogy. Electricity flows through the interconnected collagen network, finding conductive pathways. It's well studied in polymer composites, so it's a relevant model here.
And they use a specific theory for this, GEM.
General effective medium theory, yes. It models conductivity in these binary systems, insulating cells conducting collagen. It accounts for the volume fraction of collagen, a critical threshold fraction where conduction really starts, and the conductivities of both components.
Okay, that sounds like a solid mathematical framework. But why bring temperature into the DC measurements?
Because collagen itself is temperature sensitive. As it approaches body temp, around 37 degrees C, the fibers undergo increased disorder. They randomly coil, become less structured.
Like a spring uncoiling.
Good way to put it. And this structural change directly impacts their ability to conduct electricity. It messes with the wires.
So studying conductivity versus temperature lets you probe these dynamic structural changes.
Precisely. The model assumes that while the critical threshold Pc stays constant, the effective volume fraction P of conductive collagen changes with temperature.
And this leads to a key parameter, T.
Yes, the critical temperature, Tc, it's not directly measured, it's a model fit parameter. But it quantifies how quickly the tissue shifts from conducting to insulating as temperature rises. It measures the point where the collagen network's conductivity starts to break down due to that thermal disorder.
So a lower Tc means the network breaks down earlier at a lower temperature.
Exactly. And since tumor and normal tissue have different collagen structures and amounts,
They'll have different critical temperatures. It becomes a quantifiable marker of their structural integrity.
that's the idea. Tc gives us 1/2 of our bimodal electrical fingerprint, a measure of thermal stability, or lack thereof.
Okay, that covers the DC side with temperature. What about the AC side with frequency? How does that give a complementary view?
Well, AC transport captures different dynamics. It's affected by the cellular components more and how charges move at higher frequencies. In disordered systems like tissue, charge carriers behave differently based on frequency. At low frequencies, they tend to hop across gaps in the network.
Slower movements.
Right. But as frequency increases, they can jiggle more actively within the conducting grains or within the fragmented collagen fibers themselves. This transition is key.
Jiggling versus hopping.
Kind of. And the point where this transition happens, where AC conduction starts to dominate, is defined by the onset frequency, FC.
Onset frequency, FC. Okay.
Beyond FC, you see this characteristic exponential rise in conductivity. FC is very sensitive. It directly probes the extent of disorder. A lower FC means AC conduction starts earlier, suggesting a more fragmented, disordered network where charges can jiggle more freely within smaller regions.
Why does the jiggling boost AC conductivity so much?
Well, as the frequency goes up, the charges jiggle more rapidly. This increases their chance of finding spots with higher jump probability within the collagen network, effectively boosting AC conductivity.
Like shaking marbles in a box to find new paths.
That's a decent analogy. DC conductivity, remember, is limited by that single fixed path. AC can explore more options dynamically.
And how does this relate back to tumors versus normal tissue?
Crucially, during tumor progression, collagen fibers are known to get degraded and fragmented. Shorter fibers, a more disordered network in tumors.
So the fragmentation means charges start jiggling effectively at lower frequencies.
Exactly. It leads to an earlier onset of AC conduction, a lower FC value. It's a direct electrical consequence of the disease changing the tissue structure.
And there's a scaling law for this AC behavior too.
Yes, an empirically observed universal scaling law. Say bucks, where say is AC conductivity is frequency, X is an exponent reflecting how steep that rise is, and B is a constant.
So the exponent X and the onset frequency FC give us the other half of the electrical fingerprint.
Precisely. They provide a quantitative description of the structural differences, painting a picture of the tumor's more fragmented and disordered collagen network. Together with TC, it's a powerful bimodal signature.
Right, let's get into the actual experiments then. What did the data show?
They use paired samples, right?
Yeah.
Tumor and adjacent normal from the same patient. Yes, and 12 patients, so 24 samples total. Formalin fixed, the paired approach is vital for minimizing variability between individuals. Allows direct comparison.
And ethically approved tissue blocks identified by a pathologist sounds rigorous. What kinds of tumors?
Mostly invasive ductal carcinoma, N9, and some fibroadenoma, N3, which is benign. Good to test on different types.
Okay, and the measurement protocol. AC first, then DC with heating.
Exactly. Impedance spectroscopy for AC from 10 Hz up to 3 megahertz. Then DC transport while heating gradually from 21 degrees C up to 37 degrees C.
And crucially, not above 37 degrees C because collagen degrades.
Right. That would ruin the measurement. They repeated each measurement 3 times, too, for reliability.
So what did the temperature-dependent DC results show first?
They confirmed conductivity decreased as temperature increased for both tissue types. That's the positive temperature coefficient, PTC, effect. It validated using the GGM model the tissue behaved like a polymer composite electrically.
But the key difference was
The magnitude of the decrease. Tumor samples showed a much more drastic reduction in conductivity compared to normal tissue.
how drastic.
Let's look. At 25 degrees C, tumor was around 0.18 semises, normal was 0.42, but at 37 degrees C, body temp, tumor plummeted to just 0.011 semels. Normal was still way higher at 0.29 semel.
Wow, that's a huge drop for the tumor. Almost nothing left at body temp.
About a 94% drop for tumor versus only 31% for normal. And this difference at 37 degrees C was statistically significant, p 0.006. A clear electrical distinction reflecting the tumor's fragile network.
Okay, stark difference in DC. What about the AC frequency results?
Conductivity increased with frequency for all samples, as expected. They looked at normalized conductivity to compare the onset more clearly.
And the interesting part there was
The steepness of the rise. Tumor samples showed a much steeper increase in normalized conductivity compared to normal tissue.
again, pointing to more disorder in the tumor.
Exactly. It aligns perfectly with the scaling law idea. The fragmented tumor network seems better at conducting those jiggling, high-frequency charges.
Can you give us numbers?
Sure. At 15 kilohertz, normal was around 13.5 normalized. Tumor was 35.1. But at 3 millihertz, normal was about 36.4, while tumor rocketed up to nearly 3 millihertz.
Over 10 times higher for the tumor at 3 millihertz. That's massive.
A massive difference. And again, statistically significant at 3 millihertz, P equals 0.002. Another clear electrical differentiator.
So the raw data shows big differences, but the real power came from fitting these results to the scaling law models, right? To get those specific parameters, TC and FC.
Precisely. That moves beyond just observing differences to quantifying them with these elegant parameters.
Let's start with critical temperature, TC, from the DC data. What were the values?
The mean TC for normal samples was significantly higher, 42.8 degrees C. Their network was more resilient to heat. For tumor samples, the mean TC was significantly lower, 36.5 degrees C.
36.5 degrees C. That's incredibly close to normal body temperature.
Exactly. It means the tumor's conductive network starts breaking down, transitioning to insulating, much earlier right around physiological conditions. It's a direct measure of that increased disorder and fragility.
A really powerful indicator. Now, the onset frequency FC from the AC data.
Similar story, opposite direction.
Yeah.
Mean FC for normal tissue was significantly higher, 1.1 megahertz. Mean FC for tumor tissue was significantly lower, 33.5 kilohertz. P 0.019.
So tumors hit that onset frequency much earlier.
Right. The AC conduction kicks in sooner, consistent with that fragmented, disordered collagen network where charges can jiggle more easily within smaller segments. And this was coupled with a higher value for the exponent X in tumors, also confirming higher disorder.
So TME-FC together paint this really clear complementary picture of the tumor's structural chaos. Its electrical fingerprint.
That's the essence of it. This bimodal combination using these scaling law fit parameters proved highly effective in distinguishing even those closely related adjacent normal tumor pairs.
Which can be tricky with traditional methods, right? Especially at the boundaries.
Very tricky. Visual markers can be ambiguous there. But these electrical fingerprints provide distinct, quantifiable signatures that seem to draw a much clearer line.
Okay, incredible fingerprints. But how do you turn this into a practical diagnostic tool? A clear yes-no answer for a clinician. Machine learning.
Exactly. That's the next step. They used a support vector machine, or SVM, a supervised machine learning algorithm.
How does an SVM work, basically?
It finds the optimal boundary, or hyperplane, to separate two classes of data here, tumor and normal. It learns from training data to create the best possible dividing line with the maximum margin between the classes. makes it very robust for classification.
Good for small data sets too, you said?
Yes, which is often the case in these kinds of studies. So the question was, how well does the SVM perform with these electrical fingerprints?
They tested it two ways, right? Raw data versus the transform parameter.
Correct. Same 24 samples. Dataset 1 used raw data, 4 direct measurements, normalized conductivity to frequencies, DC conductivity to temperatures. Dataset 2, the transform data, used only the 2 model fit parameters, onset frequency, FC, and critical temperature, TC. Just those 2 numbers derived from the scaling laws.
And the results. You said they were dramatic.
Absolutely dramatic, especially with a specific SVM type called fine Gaussian kernel. Look at accuracy, raw data. 70% accurate. Okay, but not great. Transform data using just FC and TC, 91.7% accurate.
Wow, a huge leap just using those 2 derived parameters.
Huge leap. And look at area under the curve, AUC, how well it distinguishes classes. Raw data, 67%. Transform data, 87%. Much better separation.
But you mentioned the confusion matrix is the really critical thing in diagnostics. Tell us about that.
Yes, clinically, this is paramount. It breaks down the errors, tells you true positives, correctly finding tumors, and crucially, false negatives, missing tumors. Missing a tumor, a false negative, is the worst-case scenario in cancer diagnosis. You absolutely need a low false negative rate, FNR.
So what was the FNR here?
With the raw data classifier, the true positive rate was 70%, but the FNR was 30%.
30%. That means it missed almost a third of the actual tumors. That's worrying.
Highly worrying. Unacceptable clinically. But now, look at the transform data using just FC and TC. True positive rate jumped to 83.3%, which is very good. But the truly outstanding result, the false negative rate, was 0%.
0% false negative.
0%. In this study, using those 2 scaling law parameters, the SVM did not misclassify a single tumor sample as normal.
That's incredible. What does that really mean?
It means potentially no misdiagnoses based on this electrical signature. No delayed treatments because the tumor was called normal. It's an outstanding clinical achievement, highlighting the immense power of using these physics-based models to interpret the electrical data.
It completely validates the approach, doesn't it? Augmenting the experimental data with these model-fit parameters makes a profound difference in accuracy and reliability.
It really does. It shows the synergy between the microengineering, the fundamental physics models, and the machine learning interpretation.
What an incredible deep dive today, seriously. We've seen how combining fields microengineering with MEMS chips, the physics of scaling laws, the power of machine learning converges to offer this novel, highly accurate way to tell tumor tissue from normal tissue.
Yeah, it's a real symphony of science, as you say.
The aha moment for me is just realizing you can quantify something as complex as cancer through basic electrical properties.
Exactly. And parameters like TC and FC aren't just numbers. They are these precise electrical fingerprints of the underlying structural disorder. The fact that machine learning can read them so accurately, achieving that 0% FNR, that's the potential game changer. It really augments what we can already do, providing crucial insights at a microscopic level that other methods might miss entirely. It's getting down to the electrical fabric of the disease.
And for you, the listener, this really offers a glimpse into how science keeps pushing boundaries, finding new ways to tackle critical problems like cancer diagnosis. Imagine what this could mean down the road. Faster, more accurate, less ambiguous classifications. Ultimately, better patient outcomes through earlier, more reliable detection. Which leaves us with a final thought, a question for you to ponder. If these bimodal electrical characterizations, guided by scaling laws and AI, can delineate breast tumors so effectively, what other complex biological disordered systems might hold similar quantifiable electrical secrets? Could we apply this approach to neurodegenerative diseases, maybe detecting subtle brain tissue changes years before symptoms appear? Or perhaps early-stage infections where inflammation might alter tissue conductivity before standard tests pick it up?
The potential seems vast, doesn't it?
Mm-hmm.
Mapping the electrical fingerprint of health and disease across many conditions, it feels like we're just scratching the surface.
A truly fascinating frontier. Thank you for joining us on the deep dive.